Welcome students. For this unit, we will be reviewing the periodic table, also known as the periodic table of the elements. This table is an icon in the field of chemistry. It is also widely used in physics, biology, and other sciences. In this unit, we will cover the history of the periodic table, as well as its parts, the forms it can take, periodic trends, and also the various groups within the periodic table. First, let's take a look at the history of this important scientific resource. In 1789, Antoine Lavoisier compiled a list of the known elements at the time. The known elements were broken down into 4 groups. The chart at the bottom is Lavoisier's attempt to organize the known elements. He chose to organize them by their general properties, such as if they were an acid, a gas, a metal, or if they were commonly made from earthy materials. By the 1800s, there were many changes that occurred in the world. The first practical use of electricity was being explored. The invention of the spectrometer had revolutionized science, and all of this was the result of the Industrial Revolution. In the world of chemistry, there was an increase in the number of known elements, and by 1870, scientists had now identified 70 of them. During this period, in the 1860s, chemists agreed upon a method for accurately determining the atomic mass of elements, which laid the foundation for future development of the periodic table. In 1865, the scientist John Newlands noticed that when elements were arranged by atomic mass, they repeated properties every 8th element. He used the word periodic to describe this pattern, and he gave it the name the law of octaves. This is John Newlands' periodic table. As you can see, all the elements are arranged according to their atomic weight. Unfortunately, most of the scientists of that day were not a huge fan of his table. Newlands' arrangement did not work for all the elements. They also criticized his table because of its association with music. However, his idea of repeating properties or periodic properties was taken to heart by many scientists and expanded in their own work. Later on, the scientists Lothar Meyer and Dmitri Mendeleev, working independently, each made a connection between atomic mass and the properties of elements. Unfortunately for Meyer, Mendeleev was the first to publish his findings and as a result was given credit for the discovery. Mendeleev also predicted unknown elements in his periodic table, although the new elements weren't exactly in the correct order. Here we see the periodic table published by Mendeleev in 1869. Notice how close it is to our present-day periodic table. In 1913, Henry Moseley, a brilliant physicist, solved Mendeleev's problem by creating a periodic table in which the elements were arranged by increasing atomic number. The periodic repetition of chemical and physical properties of elements that he proposed, when arranged by atomic number, is now known as the periodic law. This is Henry Moseley's periodic table. Moseley's original table was the basis for all present-day tables like the one you see here. Sadly, this great scientist enlisted at the outbreak of World War I and lost his life at the Battle of Gallipoli on August 10, 1915, at the age of 27. Now let's start our discussion on how the periodic table works and the tremendous amount of information contained within it. The periodic table consists of various element cells. Element cells are the blocks that give information about individual elements on the periodic table. Depending on the type of table, these cells can vary regarding what information is provided. Some examples of the information that can be included in the cells are the element's name and symbol, the element's atomic number and atomic weight. Cells can be color-coded according to the group they are in. Also, their electron configuration and elemental properties can be included as well. The 2 most important pieces of information included in the element cell is the atomic number and the atomic weight. The atomic number represents either the number of protons or the number of electrons for that element. The atomic weight represents the number of protons and the number of neutrons for the element. Here is an example of a cell from the periodic table. This element's name is hydrogen and its elemental symbol is the letter H. Its atomic number is 1, which means it has 1 proton and 1 electron. Its atomic weight is 1.008, which we round to the nearest whole number of 1. This tells us that hydrogen has 1 proton and no neutrons. A column of elements on the periodic chart usually have similar physical and chemical properties. This column is referred to as a family or group. Elements in a family or group have similar properties, which is due to their similar electron configuration. Here we have highlighted column 2 on the periodic table, which represents a family or group. Just remember that a column is a vertical structure that holds up a roof. So a column on the periodic table represents the vertical family or group. A period or series is the name given to rows of elements on the periodic chart. Here we have highlighted row 4 on the periodic table, which represents a period or series. Just remember that a period is normally placed at the end of a sentence. In English, a sentence is written horizontally, so a period on the periodic table is the horizontal row. Elements in a period or series have the same energy level in their outermost shell. Just remember that although they have the same energy level, the number of electrons in that outermost shell are different for each element. In older periodic tables, a Roman numeral at the top of the chart represents the number of valence electrons. For example, elements in the column that have a Roman numeral 2 have 2 valence electrons. In this periodic table, we have highlighted the Roman numerals. You will also notice that each Roman numeral has either an A or a B after it. If there is a letter A after the Roman numeral, it means that those elements are main group elements. If there is a letter B after them, then they are considered transitional group elements. In newer tables, a whole number at the top of the column represents the valence electrons, replacing the Roman numerals. The A and B designation is still used. For example, elements in the column that have the number 7A have 7 valence electrons and are main group elements. In this example, we have highlighted the more modern numbering system that still includes the use of the letters A and B to designate whether the column is a main or transitional group. Some advanced tables have removed the A and B group designation and simply number the groups 1 to 18. However, to determine the number of valence electrons for columns 13 to 18, you must subtract 10 from the column number. For example, to determine the number of valence electrons for column 13, you subtract 10 to get a value of 3. Therefore, elements in column 13 have 3 valence electrons, not 13. In this slide, we have highlighted the numbering system that excludes the A and B group designation. Notice that column 13 is the family that has only 3 valence electrons, as we just discussed. Now let's move on to discussing the groups of the periodic table. The table is made up of 3 primary groups. They are known as the metals, the metalloids, and the nonmetals. Elements that are included in the group, called metals, all share similar properties. The properties of metals are that they are hard, shiny, malleable, ductile, and are good conductors of heat and electricity. There are some exceptions, such as mercury, which is a liquid. On this periodic table, we have highlighted in pink all the elements that are metals. Notice that all the elements to the middle and left of the black stair-stepped line are metals. It is important that you note that hydrogen is not a metal. It is only on the left side of the line because of the number of its valence electrons. The next group is the metalloids. The metalloids are elements that have the properties of both metals and nonmetals. On this periodic table, we have highlighted in yellow all the elements that are metalloids. Notice that all the metalloids touch the heavy black stair-stepped line. However, not every element that touches the line is a metalloid, such as aluminum and polonium. Our next group is the nonmetals. The nonmetals are usually found as gases or soft solids. There are some exceptions like bromine, which is a liquid. In this periodic table, we have highlighted the nonmetals in light blue. Notice that the nonmetals can be found right of the heavy black stair-stepped line and includes hydrogen. There are 2 additional special groups in the periodic table. These groups are the lanthanide series and the actinide series. The lanthanide series fits in the table after lanthanide. The actinide series fits in the table after actinide. These are taken out of the table to make it a more manageable size so the table could fit on a standard page in a textbook. Here you can see the lanthanide and the actinide series at the bottom of this periodic table. If they had been included in the main body of the periodic table, it would have made the table much wider, making it much more difficult to show. The periodic table can also provide us with the electron configuration of all the elements. Notice that all the elements in column 1 and 2 have an s subshell. You can also see that all the elements in columns 3 through 12 have a d subshell and 13 through 18 have a p subshell except for helium. Next, we will look at the various trends within the periodic table. Periodic trends are specific patterns found in the periodic table. These trends include such things as electronegativity, ionization energy, electron affinity, as well as atomic radius and others. Periodic trends are divided into two categories. The first is a standard periodic trend, which is a pattern that repeats at regular intervals such as atomic radius. The second is the quasi-trend, which is a recurrence pattern with some degree of predictability. However, this type of trend still shows some irregularity, unlike a standard trend. An example of this would be the melting point of different elements. One standard periodic trend is atomic radius. Atomic radius is the distance from the center of the nucleus of an atom to the outermost orbit. The atomic radius of the atom increases when moving down a family or group. This is due to the addition of another principal energy level. The atomic radius of the atom decreases in size as you move from left to right. This is due to the greater mass and attraction making the electron clouds more compact. This periodic table of atomic radius demonstrates this. As you can see, as we move from left to right across a period or series, the radius of the atom becomes much smaller. Conversely, as we move from top to bottom of a family or group, the radius becomes much larger. This is a true periodic trend. Next, we will look at periodic trends that deal with reactivity. Reactivity is the ease with which an atom acquires or donates electrons. The next trend we will discuss is ionization energy. Ionization energy is the minimal energy required to give up a neutral atom's outermost electrons. The higher the ionization energy, the more difficult it is to remove or give up an electron. In a period or series, the ionization energy increases from left to right across the periods. This is because of the increased mass and attraction within the atom. In a family or group, the ionization energy decreases from the top of the table to the bottom, making it easier to give up electrons. The energy levels are farther away from the nucleus. In this periodic table, we can see how this ionization energy increases from left to right and then from bottom to top. It is for this reason that we classify it as a trend. Next, we look at electronegativity. An atom's electronegativity reflects its ability to attract electrons in a chemical bond. This attraction increases across a period and decreases down a group. Electronegativity is measured using the Pauli scale. The Pauli scale of electronegativity is a widely used method to measure the tendency of an atom to attract shared electrons in a chemical bond. The scale ranges from 0.70 to 4.00. Since the scale measures electronegativity, it follows the same pattern that we discussed earlier. For a family or group, it decreases from top to bottom, and for a period or series, it increases from left to right. This is a periodic table that includes the numerical Pauli scale of electronegativity and shows both the rating and the order in which it increases as we move up and down the table. You will note that halogens on the right side of the table in family 8A is blank. That is because they are noble gases and have no electronegativity since they are complete and will not bond with any other element. In this slide, we show a side-by-side comparison of ionization energy and electronegativity. Both measure the similar capability of an atom to give away or steal electrons. As a result, you will notice that they both increase and decrease in the same pattern. Lastly, we will review the various groups within the periodic table. Group 1 is the first we will cover. This group is known as the alkali metals. All the elements in this group share specific chemical properties, such as they are very reactive and easily lose their outermost electron. They are considered the most reactive metallic family and are known to react violently with water. When they do react with water, they form alkaline compounds. All the elements in Group 1A are part of the alkali metals. The exception to this is hydrogen, It is not a member of this group. The only reason hydrogen is in 1A is because it only has one valence electron. Group 2 elements are part of the alkali earth metals. These elements get their name because they are commonly found dissolved in water. When water contains high levels of minerals from group 2, primarily calcium and magnesium, it is called hard water. In the home, hard water is often indicated by the formation of limescale on glass shower doors, faucets, in kettles and water heaters. Wherever water hardness is a concern, a water softener is commonly used to reduce hard water's adverse effects. Group 2 alkali earth metals are very reactive in water, although not as reactive as Group 1. Their reactivity increases as the elements get larger or as you go down the family or group. These are the Group 2 alkali earth metals located in Family 2A. Next are the B group transition metals. Their chemical properties can vary according to their position on the table. Some are very reactive like iron or copper. Some are non-reactive like gold or silver. Some of these elements can produce magnetic fields such as iron and nickel. The elements contained within this group can be very different and they can bond with other elements in various ways. The B group transitional metals shown here cover groups 3 through 12 on this periodic table. The next group is the inner transition metals, which cover the lanthanide series, which are rare earth metals, and the actinide series, which are mostly man-made and do not exist in nature. In regards to chemical properties, the lanthanide series elements are reactive and weakly attracted by magnetic fields. The actinide series elements are very radioactive and toxic at very low doses. The inner transitional metals are located at the bottom of the periodic table. Group 17 or 7A is known as the halogens. These elements form salts when they react with metals and are difficult to obtain in their elemental form. Halogens are highly reactive and ignite substances on contact. They are commonly referred to as oxidizers. Halogens are known to be especially reactive with hydrogen-based compounds. Here we can see the halogen group located in Family 17 or 7A. The last group we will be identifying is Group 18 or 8A, which is known as the noble gases. The noble gases do not react with other elements. They stay separate and are found normally as individual elements in nature. These elements can vary from helium, which is non-toxic, to radon, which is carcinogenic. Here we see our last group, the noble gases, located in Family 18 or 8A. This concludes our review of the periodic table that has included its history, the various parts and forms contained within, as well as the various trends and groups.